How are you guys doing? Did you guys recover from the exam? Alright, let me ask you an honest question. Do you think the exam was difficult, like on a scale 1 to 10? How was the exam?
6.
6? What was the most difficult question? The first one?
Yeah, the first one. Please on its side.
It's all about finding a fixed position to measure the, like, it was something like this, and you had, I don't know, a card. And then a card here, and both of them has somehow, you have a block here, and I don't know, I don't remember, but it was like something.
Fixed point on the ground.
Was some of them has two pulleys or?
Yeah,
Yes,
the,
too.
the second one didn't help that further.
The second one, which one that has two?
The first two.
This one?
But no,
Was not a
it
pulley.
It was attached
was just attached to it.
Okay. Anyway, so you are gonna have like something like this, right?
Yes.
So the thing is, this is the fixed point. This point is moving, and this point is moving. So all what you have to do is just to measure from here. Let's say this is y1 and this is y2. And the thing is, how many y1 do I have? I have 1, 2, 3. How many y2 I have? I have 1 and 2. So it's gonna be 3y1 plus 2y2 is gonna be equal to constant. So that is the whole thing. This wasn't like, I'm not sure if you guys measured it from here, but this is not fixed. This point is moving. And the same thing, this point is not fixed, this point is moving. I had to do something, I don't think it is like a rocket science here, but I mean, anyway, so this is how it worked in the exam. Let's say all of you guys did it wrong. Like this question, all of you did it wrong. So your average is gonna go down. I bring the average up, but let's say all of you, maybe some of you secretly solve it right. So maybe all of you complain, I was like, oh, somebody's like, oh, I did it that way. Maybe, I don't know, 10, 20 of you did it that way, so that means that the average is not down. So, but this is what I do in the exam. Like some years, the exam is difficult, students' grades are down. I'm gonna bring at least the average to 75, 80. Depends on the student's grade. But if your average already above 80, I cannot bring your average, all right? So that's what I do. So don't worry, just do your best. And there's some students in that class is gonna get over 100% in this exam. When we do, let's say all your average is down and one is already solving the whole exam right. So it's gonna get over 100 when I do the average. So don't worry about the grades. All what you have to do is you have to do your best. If you have problems in all of the questions in the exams, that means you have a really, really serious problem. I'm sure that you guys attend the class. I know we have around 73, 75 students in this class. We have like attendance around 60% or something. I'm sure that you guys at least did good, or maybe did very good. If you don't attend the class and you don't watch the videos and you don't put the effort, when you attend, you know what's going on. But the thing is, the people that doesn't attend, I was like, oh, I'm gonna watch the videos before the exams. It was like, he doesn't know what is waiting for him. We do a lot of stuff in the class. Attending the class makes you, oh, we have really, really serious stuff that I need to study. So when you watch the videos, you're watching the thing for the second time, or you double check your information. But if you watch the video for a first time, are you at home and you didn't take the whole thing seriously, you are gonna definitely have a serious problem. And the thing is, before the exam, you were like watching 10 videos, and I was like, oh, that's a lot of stuff to catch up with. And you might get desperate. Okay, I'm gonna have the equations, I'm gonna put the equations, I'm gonna get 5 points here, 5 points there. It's not gonna work. The only one that would fail the class, that you don't solve the midterms right. You don't get good grades in the quizzes. And the second midterm, all the chances are gone. I can't pass you. You know, it only happened one time. Was one of the students that he's already didn't attend the one of the midterm. So what I want to say, just do your best. Don't worry. But I have to say it again. This class is not easy. It has lots of stuff. It needs your full attention. It needs a lot of hard work. It needs a lot of practice. so that you can get, you would pass the, don't wanna say pass this class, I would like to get A. To get in this class, you have to put a lot of hard work in this. All what I'm asking, attend the lecture, be attentive to each thing that I do, and let's say there's something unclear, ask me in the lecture. I will stop whatever I'm doing and I'm gonna answer you. Whatever the question is, don't worry about the question is like somebody's gonna say, oh, that's a stupid question, that's like, don't worry about that. I take every question seriously. Like it's a big question. I'm not gonna like say, oh, we did this before. No, I'm gonna take it all the way from the basics. That's step number one. Step number two, you don't like asking questions in the lecture, I would understand that. You have the videos, you can watch the videos and go back and take it little by little. You have the textbook. The textbook actually has lots of explanation. It talks a lot about every component of everything that we are doing. So you can go back to the textbook and see how he explaining every part of the problem. And by the way, if you go to YouTube, there's lots of people explaining the same things that we are doing here. Everything, I believe in every aspect of engineering. There's lots of content out there. Pick whatever guide you like, watch him how he explained that, or watch him how he explained. I still use this till now. Like so sometimes like I'm doing something and I forgot something about math. I'm like, I would go online and search how I used to do this, all right? So there's no like excuse that you would stop and I was like, oh, that class is difficult, I'm not gonna, you will not gonna pass and become an engineer without engineering dynamics. So you have to do your best here, okay? All right, so let's continue on the topic. So right now, just to make sure we are done with midterm one, that's 25%. I was planning to, I'm not sure if you guys, we usually take the dynamics students to visit Wall of Wind. I reached out to the directory, they said that they are busy and understaffed, so we are gonna cancel the Wall of Wind visit, which it was like kind of interesting experience to see one of the largest wind tunnel facilities in the whole country. I'm not sure if you guys see it. You guys know the Wall of Wind? So it's basically, I'm gonna explain it to you. It's kind of like a turntable, like you would put a model. The size of the table is like a circle that is 14 feet diameter. And we would test like models, like small models, not like a full scale, maybe 1 to 4, 1 to 5. You can test like a room or something you can build on this, and you blow wind, and it has some sensors that you can measure wind and pressure and all the stuff. This is very important for standards when we design building. We need to know if we have a connection that connects the roof with the wall, how much load that this connection can take. So if somebody developed something new, so that's kind of like very hands-on how actual facilities or experiments look like in wind tunnels. Also, usually when we have a tall building, we have to blow some wind on this tall building to get actual wind pressures. The standards or the codes is not sufficient to come up with the load and say, oh, this is the load in this building. No, we have to make a model and we have to blow some wind and we have to measure how the wind is gonna flow around the building. So that's about the Wall of Wind facility. We're not gonna have a visit, but it's kind of just an experimental facility that can test wind loads on buildings. All right, so that's it for now. I believe our second midterm is gonna be after chapter 15. So once we get to the point, finish at chapter 14, and then finish at chapter 15, we are gonna plan our second midterm, and then the final exam will be chapter 16 and a bunch of problems from chapter 12 to chapter 15, okay? Does anybody have any questions on the grades? I'm gonna, for the exam grades, I have 73 sheets or more. I give it one time to like, not the TA, but I mean like, if I give it to the TA, you guys are gonna get destroyed. So I usually grade these exams by myself, so like I can give you more points based on your effort, because they are gonna just look on the final answer, and we all know how the final answers look like. But yeah, so I wanna like give you some more credit on your effort. Okay, so it's gonna take a little bit of time, so maybe I would work on them during the spring break, so you have to be patient with me. I'm gonna upload the model answer by the end of this week, so you can check what did you do wrong, what did you do right, so you can have a very good idea where your grade is gonna be, okay? Does anybody have any question? Yeah,
Is intern two based on fluids?
based on what?
Fluids?
Well, I usually was a different professor that teaches fluid, but he's not gonna be available this semester. So I might teach the fluid part, or I might give you different content, maybe structural dynamics part, maybe I give you different dynamics part. But we will see. If I gave the fluid dynamics part, I believe maybe one question from the fluid dynamics is gonna be on the exam, okay? All right. So if you guys remember, last week, we started work and energy. To make sure that you guys remember about work and energy when we did it last week, can work be positive? Can work be negative or no? I can do a work, negative work or positive work. I'm asking a question. So can the work be negative? Yes, right? The thing is, if you have a force that is pushes a body, if this body moves in the same direction of the force, that means the force made a positive work. However, there is some other forces that can make negative work. Like if I'm pushing this body that way, I'm over, what is resisting me? The friction. So the friction is making a negative work. What else? If I have a spring, the spring is gonna make a negative work to resist the force. If I'm bringing the body up there, my arm force is making a positive work on the body to move it up. What I'm trying to, what is resisting this force is the weight, right? So the weight is work against me. Like I have, like, let's say this body is 10 kilograms. I will not be able to move this body up until I overcome the 10 kilograms weight of work, all right? But let's say I'm bringing this body from the top to the bottom. So right now, I have this body, this weight is doing a positive work along with my arm work. Like I'm bringing it out there. So right now, it's gonna be much easier if I have this water bottle. So if I have this water bottle up there, so the water bottle is coming down easily because right now the weight is working with me. But if I'm going up, the weight is work against me. So my arm force is positive, but the weight is negative. So weight can be positive or can be negative based on where I'm going. If I'm going against the gravity, it's gonna be negative. If I'm going in the same direction of the gravity, it is positive. How about friction? Can be positive? It's gonna be always negative, right? Because the same thing, this water bottle is moving that way, friction is the other way. If I'm moving the other way, friction is in the opposite direction of the motion. It's gonna be always in the opposite direction of the motion. How about the springs? If you have a spring system, so basically, it's gonna be always in the opposite direction. If you are compressing the spring is responding to you in the other direction. If you are pulling the spring is always in the opposite direction of the motion. So spring is always negative work, friction is always negative work, weight, it can be positive, it can be negative, all right? Okay, so that's about work. How about energy? Can energy be negative? No way the energy can be negative. No one can exert negative energy. It's either zero or positive, okay? All right, so all what we were doing right now, if you guys remember, we were able to prove if you have a body and this body is moving and has a velocity v1 here and went to point v2 here, the kinetic energy at this position and the kinetic energy at this position are related. If this body exerted a specific amount of work from 1 to 2, there's a relationship says that the kinetic energy, we can call this T1 and T2. It says that the T1 plus the work done from 1 to 2 equal to T2. So the kinetic energy at position 1 plus the work done from 1 to 2 equal to T2. That is the last rule that we have. And by the way, this work can be, work comes from weight, work comes from spring, work from a force, work from friction, can be a lot of work. Like let's say this body is moving on a slope and there is a spring here, so it has to overcome the weight, it has to overcome the spring, Fs, and let's say you have a force here, this is B, friction, assuming that this body is moving down, so the friction is going up. So for this body at this position, to come to this position from position 1 to position 2, it has to overcome these, but the thing is, some of these forces are making positive work and some of them are making negative work. Let's assume this body is moving that way. This is my body. Can you tell me, does the weight make a positive work or negative work to come from here to here? Positive, because I'm going down, right? How about the friction?
Negative.
How about the spring?
Negative.
How about the B?
Positive.
Positive. If you want to find, by the way, all these forces, I'm saying the forces making positive or negative work. If you want to find the work done by each force, B has to be multiplied by a distance. Fs, which is K, have to multiply by a distance, S. And this S is the compression in the spring. F of friction has to be multiplied by the distance. Weight has to be multiplied by the height because it only matters how much the weight is moved down. Like when it comes to weight, I'm only curious about how the body moved from here to here.
So basically, everything else is with the distance x and then weight is y.
But the thing is, B is inclined, so you're only interested in the component of B, which is B
Right.
cosine theta. The B vertical, the B sine theta is gonna be crossed out with the normal force, and they both don't do work because they are normal to the body, normal to the motion. Okay? Alright, so that's actually the summary of what we have done in chapter 14 so far. So, and we did example, let's solve another one. I didn't print the question, but I'm gonna tell you the wording of the question. Example 14.5 from the textbook. In example 14.5 from the textbook, it says that there is a water slide, this is Y, and this is X. This water slide, a kid is sliding from point A and going on a curve something like this until it comes to point B. Here's A and B. And I gave you the function of this curve. This curve, y equal to 0.075 x squared. By the way, if I give you a function of a curve, that means somehow you need to find rho with this function. Rho, that means the radius. You need to take a derivative of this curve somehow, all right? Okay, and I told you that there is a boy, his mass, by the way, his mass 40 kilograms. Maybe I will not tell you it's a mass, I'll tell you a boy 40 kilogram. Once you hear kilogram, that's a mass. If you have Newton, that's weight. If you find in a problem, a boy is 100 pounds, 100 pounds, that's a weight. You have to convert it to mass if you want. Okay, so the boys start from here. Let's put the information. The mass of the boy is equal to 40 kilograms. And I told you that the vertical distance here from point A to point B is 7.5 meters. And the horizontal distance from point A to point B is 10 meters. Well, I could have actually told you one of them, and you get the other one by substituting this problem. Anyway, so let's say I give you only the x 10 meter, you can find the vertical by substituting here. If you substitute here with 10, it's gonna be 10 squared 100. 100 times 0.075 is gonna give you 7.5 meter. So you only need the x distance to get the y distance. All right, so, and I told you that this boy start from rest at A, so VA is equal to 0. Because the thing is, when you go on a slide, you start from here. You just sit and then slide. Okay, even maybe if I didn't start from rest, anybody who's gonna slide, he start from rest, okay? All right, and I ask you to calculate the normal force on the boy once he come here. Like once the boy comes here, by the way, this is kind of similar to the exam question, right? You had a body that was here and get to from point 2 to point 1 to point 2, and I'm asking about what is the value of the normal force on the body of the boy when it comes to this point. The thing is, to do this, I have to get the velocity, because to get the normal force, I'm gonna have my body like this, and I have the weight goes down, and I have the normal force going up, and I have, this is the free body diagram. Let me put the N that way. That's a free body diagram. The kinetic diagram, I'm having, since this is a curve, I'm having N and I'm having tangent. Why would I tangent that way? Because the body is sliding the other way. So I have here MAN and here is MA tangent. So that is the kinetic diagram. If I want to find AN, I know that AN is equal to V squared over rho, right? So what I need in this problem, this is a back thinking, like I'm trying to see how can I get it, the value. If I want to find the value of the normal force, I have to substitute in the Newton's second law, which is the summation of the forces in the n direction equal MAN. And N is N minus W. N is going up, W is going down, and this is going to be equal to mv squared over rho. So the weight, I have the weight, and I have the mass. All what I need is the velocity, and I can get the rho because I have the equation. All what I need is the velocity, so I can substitute in this equation. So how can I get the velocity? You can get the velocity in different ways. But the thing is, we are going to use the principle of work and energy, this, to get it. We're going to say that the kinetic energy of the boy, when it starts at point A, plus the work that the body of the boy did it from point A to point B, is going to be equal to PB. All right? So let's find, what is the kinetic energy equal to? It's half mVA squared. Can you guys tell me what is the forces that are doing work in this problem? It's either one of four forces. We just list them. Is there any weight making work? Yes, there is weight that makes work because the weight of the boy. How about spring? Is there any spring? No. Is there any external force? Is there anybody's pushing this boy to go down? No. No. Is there any friction? No. It can be, but since I didn't say what is the new friction of the surface, I didn't mention, and we usually know that the slides, they put some water to remove the friction as much as they can so the boy can move, so there's no friction, okay? If I give you, I told you the surface friction coefficient is mu equal to 0.2, so definitely you have to include the friction. So we only have weight that makes work. So this is gonna be equal to, can you guys tell me, is the work positive or negative? Positive. The boy start from here is going down. He's doing a positive work. His weight is, the weight is the source of the motion. But when the boy is starting taking the ladder to go up there, he's actually going against the gravity. So he's putting work, his body putting work to go against the gravity, and then he's gonna let himself go, so his work is gonna exert positive work. Okay, so this is a positive work, and if you guys remember, the work done by a weight is equal to the weight times y, the vertical distance that that weight is going down. It doesn't matter whatever path that you are taking. Let's say I told you that this is one way to go and this is one way to go, and actually it's gonna jump. let's say somebody's gonna jump from here. Here, the same work is here as here. So work 1 and work 2 and work 3 done by the weight are equal to each other. Because it doesn't matter what bath that you are gonna take, all of them are equal to the weight of the boy, which is 40 times 9.81 mgh. And h is gonna be equal to 7.5. And what matters is how much height that you have. So W times Y, and this is gonna be equal to half mvb squared. All right, can you guys tell me what is the velocity at A? 0. So I can cross this. So W is m times g, this is mass, so W is equal to mass times the gravity, and we are metric, so it's gonna be 40 times 9.81 times Y. How much do we have Y? It's 7.5 meter. It's gonna be equal to half times the mass, which is 40 times VB squared. So it's only one equation, one unknown. So VB is gonna be equal to 12.13 meter per second. So I got the velocity at B. Once you have the velocity at B, you can substitute in Newton's second law. It's like the summation of the inner force. You will have, this is the body, and the body at this point, the surface is something like this. So you have your weight is going down, you have the normal forces going up, and this is the free body diagram, and then this is your body. The normal force, the normal direction is always going to the center of the curve, and the center of the curve is going that way. And the tangent is always in the direction of the motion, and the body is going that way, so this is the tangent. Okay? So I have MA normal is going that way, so the same way that we have done it here, sum F normal is equal to MA normal. And all the forces in the normal direction is N minus W is gonna be equal to the mass times V squared over rho. Alright, so normal force minus 40 times 9.81 is gonna be equal 40 times V squared, which I just got, 12.13 squared. Rho, I didn't get rho, but I give you you guys remember the equation of rho? It was 1 plus dy dx all squared, and all this to the power 3 over 2 divided by d squared y dx squared. And by the way, this is the determinant of this, because the thing is, this can't be negative, the radius. Alright, so you have y is equal to 0.075 x squared. Can we get the first and second derivative? Alright, what is the inverse derivative? By the way, I can say dy dx, or you can say y dash. So it's gonna be 0.15 x, right? 2 times this. And if you wanna get the second derivative, it's gonna be y double dash, so it's gonna be equal to 0.15. All right, so the thing is, at point B, here, can you guys tell me, like I usually would put this, like the x and y direction here, like this y. Here's y and x. So usually x here is equal to 0, but x here is equal to 10. And this is actually how we get that the vertical direction equal to 7.5. Because we assume that the 0 and 0 is here. So that's why we get this is equal to 7.5. So x at point B, like if you wanna find this at point B, so this is where x is equal to 0. So basically it's 0.15 times 0, equal to 0. And here, this one is gonna be equal to 0.015 because it's constant. So if you wanna get rho is gonna be equal to, this is 0. So it's gonna be equal to 1 over 0.015. And this is gonna give you rho equal oh, sorry, this is not 0.05, this is point, because the thing is, once I take the derivative of this, it's gonna give me this number, 0.15. 0.15, this is gonna give us 6.67 meters. So I got rho, so I can plug rho here. 6.67. Then I can get n. Once you are done with this, n is gonna be equal to 1275.2 Newton. That is the normal force at this position.
Professor,
Yeah.
can you do the calculations on how you got VB? Because I was trying to do it and I don't get 12.13 for VB.
Alright. Did you multiply 40 times 9.81 times 7.5?
Oh, because you wrote plus.
No, sorry, this is, because the thing is, there's no plus here. That is gonna be W times Y. All this is
Oh, okay.
multiplication.
There you go.
Yeah. So W is 40 times 9.81, multiplied by Y, which is 7.5.
That makes sense. Thank you.
Alright, so I believe right now we are done with this part, the principle of force and energy. So now we are gonna shift to something that's called the conservation of energy. I believe you guys, yeah.
Isn't it already in the y direction? Why do you times it by?
The weight is in the Y direction. Well, the weight is moving on this curve, but the thing is we multiply the weight by the vertical distance. Oh, you wanna say that the Y is negative?
No, like, it's like, the weight is going straight down, so it's already in the y. I was just wondering why you times it by 7.5.
Because 7.5 is the Y direction, is the height of the Y direction. So, I don't understand your question.
Because in the previous chapters, when you were doing the Fy forces, you were not multiplying it by the y.
Because the thing is, we are only doing forces. When we do work, like this equation is a work. Work is a force which is W, the weight, times distance.
Okay. Oh.
So weight is multiplied by the distance, which is the Y, the vertical Y that we have.
Okay.
So this is like kind of different concept, like if we have work, so it's force times distance. So every force, like if we have, let's say a spring, the spring is gonna be F, the force in the spring is gonna be K times S, that's a force. But if you wanna make it to work, it's gonna be half KS squared, because we have to integrate it. And if it's a force B, FB is gonna be multiplied by the distance S. So here, any force is gonna be multiplied by a distance, but make sure that this distance is in the same direction of the force. Like if B is inclined, you are gonna get the horizontal component that is in the same direction of the force. Okay? All right, let's talk about the conservation of energy. All right, chapter 14.5, conservation of energy. There's some forces that are conservative and some forces that are not conservative. What conservative mean? It means like you can convert them from one shape to another. Like let's say this water bottle is here, is having a potential energy. What is the potential energy? That it can fall on the ground. So let's say, once I put this water bottle here, it lost all their potential energy. It can't fall anymore because it's already on the ground. But once you grab it up, you are giving it more energy, kinetic energy, and then you put it here and you convert all the energy into potential here. So that what is the potential that this one can fall? This right now it falls on the ground because it has a potential to fall. This is called conservative potential energy. So weight is one. Say here. Gravitational potential the gravitational potential energy, usually potential energy, we put it was letter V, and V here with gravity is called Vg, and it's equal to mgh. What is mgh? mg is the weight, right? And h is the y. What is the y position of the body? So it's the same thing like we have done here. But the thing is, in this case, you have to pick a datum. Like, let's say, my body is like, I have a rock, and this rock is coming downhill, all right? So at this position, it was here. Let's say it became here. Did it gain more potential energy or less potential energy? Less potential energy. And it came here, he's keep losing its potential energy. But the thing is, all the potential energy depends on the datum that you pick for your problem. Like, let's say I'm measuring the height from here. So that is my datum. What is this datum? That is the ground surface of the earth. If this is the ground surface of the earth, so zero potential energy at this point. So if your body above this with a height W or Y, so right now your body has a positive potential energy. If it's below the datum, like something like this, so this is negative Y, so the body when it comes here, it has a potential energy of negative W times Y. So with any problem, if you are going to use the principle of conservation of energy, you have to pick a datum. This datum can actually be here, but this datum is going to stay for the whole problem. You cannot change it during the problem. Once you pick a datum at a position, you cannot change it. Okay? So you take the datum and you measure the height from this datum, and this is going to be potential energy from this specific datum, right? Okay, so that is for the gravitational potential energy. Number two, it's called the elastic potential energy. We call these conservative energy because they don't lose it. Like if you lost your potential energy, you definitely converted it to kinetic energy. Your velocity here was zero, and once you went downhill, your body has a velocity, different velocity. So you converted your potential energy, like this body has a velocity zero here. Once I pushed it, and it went down with velocity, and this velocity is increasing with the gravitational acceleration, so it gains the potential energy into a different type, which was the kinetic energy. Same thing with the spring. Let's say you have a spring here, and by the way, this spring is elastic. Elastic means if you push the spring from a specific point all the way that way, it's gonna, once you leave it, it's gonna come to the original position. If this is inelastic spring, that means once you push it, it might not come to the original position. So what we deal with here is elastic springs. So let's say you have a spring here, and this is a mass, and you compress your spring to go all the way as here. So we say that the V of the spring, we call it VE, like to represent elastic. So this is VG, and this is VE, equal to half K times the delta in the spring squared, which is representing like the work done by the spring. It doesn't matter if this is spring under tension or under compression, the energy is always positive. So if you push your spring come at this position, it has an elastic potential energy. All right. what is this elastic potential energy is gonna make to this spring? Once you leave it, it's gonna come back to the original position here where the energy is equal to 0. Let's say you take your spring, your body's here, and you extended this spring to go to this point, S. It still has the same elastic energy if S here is equal to the S here. So it doesn't matter if S is positive or negative, it's gonna have the same kinetic energy, which depends on how much delta. And delta is the measured length from the unstretched length of the spring. So this is the unstretched length from the spring, and you went delta that way. Alright? That's why we have a square here. There's no way that the elastic energy in a spring is going to be equal to negative, because K is always positive, and delta, even if it's negative, is going to be squared and it's going to become positive. Alright? Okay, so that is the elastic energy in a spring. So the rule that we have here So the rule that we have here, we say that the summation of the kinetic energy of anybody plus the potential energy at a specific point is equal to the kinetic energy at point 2 plus the potential energy at point 2. What does this mean? Let's say that you have, for example, a body is going to fall, like let's say something like this. And this body has a mass m and it's going to go that way. So at point 1, where the body starts from rest, but it has a potential energy. What is this potential energy? The spring is stretched and also has a weight. The weight is going to go down. So can you guys tell me? Okay, don't tell me. Here's 1 and here's 2. So the energy at point 1 and the energy at point 2 are related. So what I'm saying here is the kinetic and the potential energy of this body at this point is going to be equal to the kinetic energy and the potential energy at this point. They are going to swap each other. How? The body here doesn't have any kinetic energy. It started from rest, but it has a lot of potential energy. What are they? It has a spring, because the spring is stretched. It's going to pull the body back. And also has what is it? The gravitational potential energy so this body can go down. But once the body goes down, he's keep losing the potential energy. The weight keep losing potential energy, and also the spring keep getting to its unstretched length until it loses all the energy in. But the thing is, this energy is converted into kinetic energy that makes this body move, and is going to have a velocity v2. So right now it shifts from velocity v1 is equal to 0 to have a velocity v2. So this is your body. Your question here should be, how about the non-conservative forces? Like let's say, what if I have friction? What if I have an external force B? How can I represent that? So if you have non-conservative forces, like once you put them in the body, you cannot get them again. Like here, I converted the potential energy into kinetic energy, but let's say the friction is not conservative. Like once this body moves, the friction happens, doesn't convert it to other energy. You lose them. And same thing if you have a force. If you have external force B, once you put it in the body, it's gonna go inside the body and make a velocity V. So since they are not conservative, you can put them that way. T1 plus V1 plus the work done by the non-conservative force from 1 to 2 is gonna be equal to T2 plus V2. T is the kinetic energy, V is the potential energy, and this is the work done by the non-conservative forces. You will tell me, but this is actually looks like this one. Yeah, you know what I did? What I did here, I take from this work, I took out the work done by the weight and the work done by the spring, and I put them here and here. And I left the one that are non-conservative. So that basically this is kind of similar to this, but I just take the weight and the spring out of this and I put it here outside. So this is called the conservation conservation of energy equations. So the general rule is this, equation number 2, but if you don't have any non-conservative forces, like if you don't have friction or you don't have external force, you can cross this and you're gonna end up with this equation. So let's solve a problem and see how this stands out. An easy problem and a very difficult problem. Let's solve the difficult one. This example is not in the textbook, so. So this example, let's look at this mechanism. You have a bar and you have a collar that can run on this bar up and down. And this collar is attached to a string, and this string runs on a pulley C. And the pulley C, the line from pulley C and the bar have a right angle, and this bar is at angle 30 degrees from the horizontal. And the cord that we have here, the string has a force B equal to 50 pounds acting on this bar. So what is gonna happen here? It says a 30-pound collar, so the weight is is equal to 30 pound. It starts at rest at point A. So point A here is at rest. So we have VA is equal to 0. Slides friction free, so there's no friction, up to AB here. And compress this spring 6 inches. So once this force, the 50 pounds, start pulling up, is there any spring forces here? No. Only the spring force is gonna kick at some point here towards the end, and then it's gonna compress the spring 6 inches and start from here up to there. Okay? And it says that the K of the spring is equal to 200 pound per foot. What is the velocity at B? All right, so the thing is,
Where's B?
what is your question?
Where's B?
B is here, sorry. The thing is, one main question, you will be like, how can I know I'm gonna use conservation of energy, or gonna use work, or gonna use Newtonian kinetics? The thing is, let's say I'm asking for V. Once you hear the V, the velocity, definitely you would go to the kinetic energy, because the kinetic energy equation has half mv squared. So this is the first equation that I would go to. But if I told you, find the acceleration, so probably you can use this and use the V to find the acceleration. Or you can use the chapter 13 and get the acceleration right away from Newton's law. Summation of the forces equal the mass times the acceleration. So you don't have to use the energy equation at all. And actually we are gonna take in chapter 15, impulse and momentum. And impulse and momentum is mass times the velocity. So you can use impulse and momentum, or you can use chapter 14, the conservation of energy. So that's when you have problems that involves velocity, okay? So once I tell you velocity of B, you'll be like, the first thing you are gonna think about it. The body starts A at rest, so the kinetic energy here is 0. Can you guys tell me what the forces that are making energy here?
The string,
The string, what is the forces in the string?
50 pounds.
50 pounds. So this string has 50 pounds here, right? Because the thing is, if the string has 50 pounds here, if you cut at any point in this string, what is the force that is gonna be here?
50.
B equal to 50. What is the problem with this force? Let's say this is the bar, okay? And this is point A, and this is point B, and this is your bully somewhere here, and is bullying A. So the thing is, the force A, like the spring at this point, B is in this direction. Once, let's say that the body moved to here, what is happening to the B?
It's changing.
It's keep changing the direction. So the thing is, theta is not constant, right? So here you have theta 1, theta 2, theta 3. So the thing is, this is one of the biggest challenges that I have to find out. If B is has a constant value, by the way, I can tell you B is doesn't equal to 5. B is equal to 20 sine theta. Keep it changing. That's gonna be very, very difficult. Once you have the two components that are making work are changing, you will have to go to the very simple principle that the d work is equal to the force F times dr. This is how we actually prove the work where it came from. And the thing is, to get the total work, we have to integrate. So to get the work, it's gonna be, if F is constant, you are gonna take it out. And then you are gonna say cosine theta, because the thing is, let's say that the dr is this way and the velocity is that way. So F, and this is dr, and this is the angle between them, theta. And if you want to multiply them, dot product, can you multiply them? Get the dot product of these two vectors. It's gonna be the magnitude of the first one times the magnitude of the second one times what?
Cosine, right?
Cosine theta, all right? So the thing is, here you have F cosine theta times the magnitude of dr, actually you can put it as a ds or dr, whatever you want, the magnitude. And then you have to integrate it from theta here, theta 1, up to theta 2, right? So you have to find what is the value of theta here, and what is the value of the theta at the end, which is like 90 degrees. Theta here, didn't start from 0, it started from a specific value, which is, you have to find, this is 30 inch, and this is 40 inch, so you have to find the value of theta. So this is how you can find the force that is done by the string. So, doing this, once you integrate the work is going to be equal to the integration of the force in the spring cosine theta times by ds, and we have to convert. The thing is, here's the problem. What is the variable here that is changing? Theta, but what is the d that we have here? This is not d theta. So it's either one of two things. You have to convert theta into s, or you have to convert ds into theta. So let's find out. Let's actually find what is the general value of theta. Like, let's say here's the rectangle, and here's, let's say I'm looking at this point. This is theta. This is gonna be always constant. It is 30 inch, right? And this is actually s. This is s, where I wanna find out how much the body moved. So if you wanna find cosine theta, or tan theta, let's say tan theta. Tan theta is equal to the opposite over the adjacent, right? So you have 30 over s. This is tan theta, 30 over s. So if you want to find the value of theta as a function of s, so theta is equal to tan inverse 30 over s. So right now I convert theta. So basically this integration is going to be equal to b, which is equal to 50. B is going to be always constant. What it changes the value of the b component is the theta, because it's theta changing. So I have this as cosine tan inverse 30 over s. Why did I converted this? Because that is the value of cosine theta of theta, which is equal to tan inverse 30 over s. And here I convert ds. What did I do here? I converted theta into a function in s, and I have ds here. So right now the value of integration is not going to be from theta 1 to theta 2, because right now I have everything is in s. S starts from 0 until it goes to 40 inch. 0 to 40 inch. By the way, since I gave you here the units, this is something to be careful about. I give you K in terms of 200 pound per feet, and all the measurement here in inch. You either convert this to pounds per inch, or you convert the inches to feet. So what I'm gonna do, I'm gonna convert every inch to feet by dividing over 12. You will tell me, how can I get this integration? I will tell you, use the calculator right away. Do you know, guys, how to do integration on the calculator? You basically write this. You will have a sign of limited integration on your calculator. Put 0 up to 4 over 12. Then put 50 cosine tan inverse 30 over x. Pick any variable in your calculator, x, y, whatever, and put dx at the end. And then you are gonna end up solving this. You guys have solved any integration on the calculator before? You can do any integration of any variables on your calculator. So I would allow you to do it. And this is going to be equal to 83.33. Wow, that is, sorry, that's not going to be bound, that's work. It's going to be bound feet. All right, so this is the first force that makes work, and this work is positive or negative. All right, this body is moving up, and this force, who's the one who's pulling this body up? The B, right? So B is always the one that making positive work. What other forces that make work? Yeah.
That's supposed to be 40 over 12.
40 over 12, that's a unit conversion from 40 inch to feet.
Oh, okay.
Okay? All right, so what is the next force that makes work? I only have one force that makes positive work, which is the, yeah.
Question, that 30 over there, is that, in inches, or is that in the inverse tangent of 30?
Excellent, so this one should be 30 over 12 too. Because I converted this one, I have to convert all the units, thank you. All right, so the second step is how to get the other type of forces that make work. Can you guys tell me what other forces that can make work?
Spring gravity.
Spring and gravity. Gravity, how? This body's gonna move from here up to all the way to B. So the work done by W is gonna be the work done by W from A to B, which is it positive or negative? Negative, because it's going up. So it's gonna be negative W times the Y distance. Okay, what is the Y distance? You have to find this distance from here to here. What is this Y distance? Can you guys find this Y distance? If you know this angle is 30, and you know that this is 40 inch, so what is the value of Y? It's gonna be 40 over 12, so that we can convert it. Sine or cosine? Sine 30. It's like a triangle like this, has this 30 degree and has this 40 inches, and we are trying to find this value, which is this. So this is gonna be equal to negative 30 times 40 over 12 sine 30. I found out the work done by the weight. Does any other force make work? There is. The thing is, the weight is gonna be by itself until it comes to this point. And once the spring gets compressed, it's gonna make work. Is this work is positive or negative? The work done by the spring is gonna be always negative, right? Because you are going against the spring is pushing you back. So the work done by the spring is equal to negative 1 over 2 K times S2 minus S1. And all this is squared, like S2 squared minus S1 squared. So this is gonna be equal to negative 1 over 2. K is like 200. And here S2. All right, the spring was uncompressed here at S1, so S1 is equal to 0. S2 is equal to 6 inch, so you are gonna have 6 squared. And by the way, you have to divide this over 12, and all of this is gonna be squared, so that will be the units consistent, and you can find this value. So right now we found all the values that makes work. Okay? So let me continue here. All right, so the main rule that we have for the this problem is like I'm using T1, the kinetic energy at position A, I'm gonna call it TA, all right, plus the work done from A to B equal to the kinetic energy at B. So here up to there. So the kinetic energy at A is half mVA squared. And VA is equal to 0. Already I told you that the body starts from rest. Plus the work done from A to B. The work done from A to B is this. The work done by the weight by the force B. Let's put this B. And here is the work done by the weight and the work done by a spring. So this is gonna be equal to U B plus U spring plus U weight is gonna be equal to half mVB squared. And we got all this. This one is gonna be equal to 0. UB is equal to 83.33 plus U spring. I didn't calculate it exactly. Did you guys calculate this one? multiplied by 6/12 squared. And the one done by the weight is -30 times 4/40/12 times sine 30. All this is gonna be equal half. And by the way, the mass, I give you the weight in pounds, so the mass is gonna be equal 30/32.2, and this is gonna give you VB squared. This is one equation and one unknown, so basically you can get the value of VB, and this is gonna be equal to 4.23 feet per second. All right, so here I use the principle of work and energy. Can I do the same thing using the principle of energy conservation? Yes, I can do that. What is the principle of energy conservation? Look, this is the rule. Half m v1 squared plus n gh1 plus half k delta 1 squared plus any forces that do unconservative work, 1 to 2 unconservative, equal to half m v2 squared plus m gh2 plus half k delta 2 squared. That is the general rule of the conservative work that we put. I was here in a little bit. I just expanded the weight, expanded the spring, and did the same thing here. So let's do it. Half mv1 squared, that's 0 because the velocity is equal to 0. But the thing is, before I do this, I have to make a data. The data that I'm gonna make, I'm gonna say that this is the 0, the data. Can you guys tell me what is the potential energy here?
0.
0. So mgh here is 0. 1. How about the spring? Is the spring compressed at this point?
No.
No. So this is also gonna be 0. So I'm gonna only end with the unconservative force, which is B, which we already got it, 83.33, 83.33, which is the external force. The only conservative force is the weight and the spring. All this is gonna be equal to half mvv squared. M is equal to 40. 40 over, because it's, sorry, it's 30 pounds. So it's gonna be 30 over 32.2. Okay, V2 squared, I don't know it. I'm gonna put it here. MGH2, so this is gonna be equal plus, M is gonna be 30 over 32.2 times, actually times 32.2. I could have put the weight right away. H2 is this height that I just calculated from here to here, and we did it here. That's why the height from the datum, which was 40 over 12 sine 30. So I'm done with MGH2. How about the spring? The spring at point P, at this point, is gonna have an energy of half the spring stiffness, which is 200, times delta 2, which is 6 over 12 squared. Just one equation without all the stuff that we have done here, and you can calculate V2, and you're gonna get it 4.23 feet per second. If you look at it, it sounds like they both are the same thing. Like, look here, what we did was the weight. We calculated this minus this. But the thing is, we just separate them. Like, rather than saying mg h1 and mg h2, we did it mg h1 minus h2. And here, half k delta 1 squared, half k delta 2 squared. If you put it the other way, it's gonna be half k delta 1 minus delta 2 squared. So it's kind of the same concept, but we just expanded it. So the only thing that might take work from you is the unconservative forces. Right? I know it's a really difficult question. Might not give it like an exam to solve. As you see, like in the exam, you don't do all these calculations. But I mean, like, it's really good example that you can learn how to do work and energy, how to do conservation of energy. Yeah.
That's V2, right? I'm wrong.
This is V2. And this is V2.
So this, What was the second equation of electrical finding?
What is what?
The equation you just finished, I understand what the blue one is, I'm not.
This
sure.
is the conservation of energy equation. That the kinetic energy plus the potential energy plus the work done by unconservative filters equal to the potential energy. Look here, this one is T1. This one is VG1, and this one is VE1. And here is T2, VG2, and VE2. I put this equation a little bit. T1 plus V1 equal to T2 plus V2. And this is the force done by unconservative, the work done by unconservative. I just expanded it.
For the VG2, the H is what, height?
Is the height, yeah, is the height that this body moved from here to here. That's the vertical height.
Oh, okay.
What is the H from here? Which is this one that we just got.
Oh, okay.
One.
Oh, okay.
Okay, that's it. I think it's red like all
And I didn't turn my whole seat around.
This is whole, not angle, this is red. You know how to? Yeah. Alright.